Hi, I'm Mason Vale from Boise State University. In this video, we will be introducing the basic concept of recursion and recursive programming. Thinking recursively is really about pattern recognition and deconstructing a complex problem in a stepwise fashion until we arrive at a simple version of the problem that's so simple we know the answer and can immediately give the response. So for this example, we're going to look at something fairly recognizable, a comma-separated list of numbers. So if we think about the smallest list that we would recognize as a list, we might say that a single number is sufficient to be recognized as a list. In this example, number 37 is all by itself a valid list. It's just a very short list. So we might say that a list, the definition of a list, could be a number. But in order to add more elements to that basic starting point of a single number, we can recognize that each list longer than a single element is a number, a comma, and something else that we've already identified as a valid list. So 40, 37, a number, a comma, and the 37 that we already identified as a valid list is also a list. Each additional number is a number, a comma, and attached to something that was already identified as a valid list. 24, comma, is attached to the front of something else that we would have identified as a valid list. So building up, we would start with the simplest case, the simplest value that we would recognize as a valid list, and we can see that we can append a number and a comma to that valid list stepwise to build up to the full list. Going the other direction, if I needed to do something with this long list, I could start by recognizing that I can deconstruct the 24 and the comma. I can remove the 24 and the comma from consideration and leave myself with something that is a smaller list. It's a simpler version of the original construct. Likewise, if I remove the 88, I get a shorter list, a 40 and a 37. And if I remove the 40, I get back to a 37. A 37 is the simplest possible case, so it can't be deconstructed any further. Notice in this recursive definition for a list, we have one part that is a standalone part. It's as simple as it gets. A number can't be deconstructed any further. But the definition of a list includes itself as part of its definition. This piece down below is referred to as the recursive portion of the recursive definition. So list is self-referential. Every recursive definition must have at least one non-recursive part, one of those stopping points, those simple cases for which the answer is immediately known. Those are referred to as base cases. Without a base case, there's no way to know when I can stop deconstructing a problem into a simpler form. It's also critically important that the recursive portion of a definition is getting me closer to a base case when I apply it to deconstruct a problem. I must be making progress toward finding a base case. Let's look at an example of a recursive definition from mathematics. Factorials for any positive value of n, any positive integer n, is the product of all of the integers from 1 to n inclusive. Now, n factorial can be expressed recursively as both a base case and a recursive case. We're defining 0 factorial to be 1. That's not an accident. That is actually the case because of the n choose k formula. But we're going to say that our base case is 0 factorial. If we have deconstructed our problem and arrived at an n of 0, we will say that the answer to 0 factorial is 1. So if we recognize the base case, n is 0, we will respond with the answer 1. But if we have a positive integer, anything greater than 0, we define the value of n factorial to be the value of n times, here's the recursive part, n minus 1 factorial. So we're going to reapply our factorial definition for a version of n that's 1 less than the original version of n. The original value may have been 3, but we're going to use 3 times 3 minus 1, 2 factorial. And we would reapply this formula, reapply this definition. So we would take our original value of n and continually deconstruct the problem by using that value of n and multiplying it by the recursive piece, n minus 1 factorial. Let's say we did start with 3. If we applied 3 factorial, we would check to see if the value of n is equal to 0, our base case, and it isn't. So we would say that the value of 3 factorial is 3 times 2 factorial. The 2 factorial comes back in at the top, and we check to see if 2 is equal to 0. It's not, so we'll reapply the recursive portion. 2 factorial is 2 times 2 minus 1 factorial, 1 factorial. So we come back to the top again, we check to see if 1 is our base case. It's not. So 1 factorial is 1 times n minus 1 factorial, 0 factorial. In this last application, we find our base case and we start to return the partial solutions from all of these deconstructions and rebuild to the original answer. So 0 factorial is 1. We would return that in this position. So 1 times 1 is 1, and the answer to 1 factorial is 1. The 1 factorial is returned to the place where we were trying to calculate 2 factorial. So 2 times 1 factorial, or 1, is 2. So the answer to 2 factorial is 2. The 2 factorial is returned to the place where we were asking the value of 3 factorial. So 2 times 3 is 6. That was our original call. We now know that the answer to 3 factorial was 6. The way we make use of recursive definitions in programming is by writing recursive algorithms into a method, because a method can call itself recursively. Each recursive call should pass in as an argument to the method a simplified version of the problem, deconstructed using the recursive definition for the problem at hand. So each recursive call should be a simpler version of the problem, getting us closer to a base case. The code has to handle both base cases and recursive cases to avoid infinite recursion, and the base cases must come first. I don't want to apply a recursive case if I was past a base case. The call stack, the method call stack, is holding all of the partial solutions to the problem that's being deconstructed until the last method call arrives at a base case and can start returning those partial solutions and reconstructing the final result. Once the call stack is unraveled all the way back to the original method call, the final piece of the deconstructed puzzle can be put back together again for a final solution. Another example of a recursive algorithm that we can apply using programming is summation, calculation of the sum of all integers from 1 to n, calculate a running sum. Now, obviously, you can probably think of other ways to do this, superior ways. There's a formula for this. We could also write a loop to do running sums. But if we're thinking recursively, we can recognize that the sum of all numbers from 1 to n has a recursive definition. If my n value is 1, the sum of all numbers from 1 to 1 is simply 1. I can recognize that as a base case and return the answer that the sum of all numbers from 1 to 1 is simply 1. No calculation necessary. But if my n is greater than 1, the sum of the values up to n would be n plus the sum of the numbers up to n minus 1. This is very similar to our factorial problem. So we can take this definition and write it into a method. And here is the method. Public int sum. It's going to return an int that is the value of the sum of the numbers from 1 up to the number that's passed in as an argument to the sum method. We're going to return a result that reflects the sum of the numbers up to that number. We begin by checking for a base case. If the number that was passed in is 1, that was our base case and the result will be 1. If the number that was passed in is not 1, then we apply the recursive definition. The result is the sum of the number that was passed in and the result of calling the sum method using num minus 1 as the input. This is the recursive piece. This is the sum method, and the sum method internally calls itself. So the second call to sum in a recursive call would be added to the top of the call stack above its predecessor. Eventually, at the top of the call stack, there will be a call to sum in which num minus 1 does equal 1. And at that point, the results would be returned through the call stack until we arrive back at the original sum method call, and the original number will be added to the sum of all numbers smaller than that original number, and that answer will be returned. Let's look at the call stack for a call to sum using 4 as our original value. When we call sum with the value 4, we compare it against the base case, which was 1. 4 is not 1, so we'll use the recursive case instead. Sum 4 will return 4 plus the result of calling sum 3. So sum 3 is added to the top of the call stack. We examine the 3 and compare it to the base case of 1. It's not the base case, so we'll apply our recursive definition. The value of sum 3 is 3 plus the return value of sum 2. Sum 2 is also not our base case, so the result of calling sum 2 will be 2 plus the result of calling sum 1. When we make the call to sum 1, we arrive at our base case. The number that was passed in equals 1. So the return value from sum 1 will be 1. So that comes off the call stack, the value of 1 is returned, and sum 2 will return 2 plus 1, 3. So the 3 is used in the calculation of sum 3. 3 plus 3 is 6, and we return that to sum 4. And the final result of sum 4 is 4 plus 6, or 10. The organization of all recursive methods follows the general recursive algorithm. You begin by checking for a base case. If the problem can be solved for the current version of the problem passed in as an argument, the base case, solve it and return the answer. Only if you haven't solved the problem do you recursively apply your algorithm. So the first step of the recursive portion is to deconstruct the problem into one or more smaller versions of the problem and recursively apply the algorithm to those smaller versions. When those answers come back, you can combine the solutions to the smaller problems to get the solution to your original problem. Just as a note of caution, all of the examples that we're looking at here are called direct recursion. A method calling itself is direct recursion. It is possible, however, that you could create a sequence of methods that create sort of a cycle or a loop, where, say, method 1 calls method 2, calls method 3, which calls method 1, which calls method 2, method 3, and so on. This is generally a mistake. It's poor program design. It makes it extremely difficult to understand what's going on, and it makes debugging extremely difficult. You would be better off if you have a sequence of steps, a sequence of subroutines, to create one high-level method that contains each of those subroutine method calls and then recursively calls itself directly, so that there's one clear method controlling the entire process that is the recursive method. In thinking about alternative solutions to a problem, we need to compare recursive solutions to iterative solutions. Iterative solutions are those that involve loops. So first of all, every problem that could be solved recursively could also be solved iteratively. There's nothing you can do with recursion that you could not accomplish using iteration. Adding to that, recursive solutions often have a little more overhead involved. Those method calls take time, they take processing time, and they often cause more memory use than an iterative solution. So recursive solutions tend to lag slightly behind iterative solutions in performance. Now, just as a note, that generally does not change the order, the algorithmic order. If we think of the order of an iterative solution being defined by the number of loop repetitions, the order for a recursive method tends to be the number of calls in the call stack, and those two numbers are typically the same. So why are we still talking about recursion? Well, we have to think about our priorities when we're programming. Our number one priority when we're programming is program correctness. If the program doesn't do what it's supposed to do, we don't care how slick or elegant this solution might be. Our second priority is easy to understand, clear, maintainable code. It's about code maintenance, long-term code maintenance and understanding. Efficiency generally comes in third. So we would only be concerned with getting the maximum performance if our real-world application is simply not fast enough for our needs. We would prioritize understandability over every last clock cycle. So it turns out that there are problems that are more easily understood and elegantly expressed using recursive solutions rather than iterative solutions. A couple of classic examples of problems with really elegant recursive solutions are maze traversal type problems and the Towers of Hanoi puzzle. Maze traversals include many problems that can be defined in terms of a starting state and a solution state, but the sequence of necessary steps to get from start to finish is unknown. These types of problems examine the current state to see if it's a solution or an invalid state, like a dead end. Those are two possible base cases. Or it recursively generates new states that potentially move one step closer to a solution according to the available valid moves. The Towers of Hanoi puzzle involves some number of stacked disks that must be moved from a source peg to a destination peg, with a third peg serving as a temporary peg, with the restriction that only one disk can be moved at a time and a larger disk can never be placed on a smaller disk. While this problem might sound challenging, especially as the number of starting disks is increased, the recursive solution can actually be expressed in only a few statements. If n is 1, there's only one disk, you simply move the disk from its source peg to its destination peg. That's the base case. If it's not the base case, then you move to the recursive case, which is 3 steps. First, you recursively move the n-1 disks off of the nth disk on the source peg and onto the temporary peg using the destination peg as the temporary peg. Then you move that nth disk from its source peg to its destination peg, because you've moved the n-1 stack off of that disk. And finally, you recursively move those n-1 disks off the temporary peg onto the destination peg on top of the largest disk, using the source peg as a temporary peg. You have to recognize that in each of those recursive steps, the first and third recursive step, those n-1 stacks are simply smaller versions of the original problem. So you have to consider the source, destination, and temporary pegs from the perspective of each individual problem, but that allows you to break down any sized stack of disks into smaller and smaller stacks and move everything out of the way appropriately. With this simple algorithm, the Towers of Hanoi problem can be solved for any initial size stack of disks.